So before I start just executing code, which will be the largest part of this, I'm gonna also introduce this definition of explaining a prediction from the Lime paper, which is presenting a visual or textual artifact providing a connection between the features X and the model's predictions Y. It sounds kind of vague, but it could be like for images you have some so up here you have the actual images, and then they compare three different methods for somehow explaining to a person what the model is looking at. Like, oh, torch. It's predicted that it's a torch, and that's here, and it predicts that this is an umbrella, and that's here. Explaining images is like its own thing almost, so I will not talk about that either. And the same thing for text. This is from Lime, where this is from the 20 news groups data set, where it has to predict what news group a text comes from. And here it has predicted that some text is likely from the Christian news group. And it shows that Luther and Catholic are the features that make it more likely that it's from the Christian, and Deer and Heck make it less likely that it's from the Christian group. And then it also shows an explanation for the next most likely category, Mid-East. And finally, for what I call tabular data, like just a table, CSV file with numerical and categorical features. You can have visualizations like this, where you see that the mean value is 24.41, and then the features in red are contributing to a higher value, and the blue ones are contributing to a lower value, and in different proportions. So this is a kind of artifacts that they are talking about. Yeah, and I also wanted to highlight this ebook, Interpretable Machine Learning, which is really nice. It goes through a lot of the stuff that I'm going to show here, and there is an associated R package for it, which is called IML. So let's look at some code. So I'm going to go through some of these things that I showed in the previous slide with different kinds of explainability. Feature importance is the first one, and there are many packages that do that in different ways, but some of them are IML that I mentioned, Daleks, and Random Forest Explainer. Can maybe look really quickly at some web pages. So here is the page for the Interpretable Machine Learning book, where it talks about definitions, interpretable models, model agnostic methods, the future of machine learning, stuff like that. The Random Forest Explainer package that I'm going to show has a nice vignette that explains how to use it. So, can you see this, the code? So I'm just going to show a lot of different packages. Maybe went a bit overboard with the packages, but hey, it's fun to try new packages. So Daleks, IML, PDP, partial dependency plots, which we'll talk about later. Random Forest. Actually, it's much better to use Ranger, as Holger said in the previous talk, but these data sets are really small, so it's fine with Random Forest Explainer, XGBoost, and XGBoost Explainer. And we'll look at two different data sets. The Boston data set, which is quite well known, but has cryptic feature names, so I've got some explanations here, just in case I forget what they mean. In this data set, you're supposed to predict the median value of apartments, I guess, based on features such as crime per capita and nitric oxide concentration, average number of rooms per dwelling, and things like that. So if we just run a random forest, you see it was really fast because it's a small data set. Just the regular random forest method in R. Out of the box, it has this var imp plot function where it shows two different kinds of feature importance plots. One is based on like seeing how the accuracy is affected by shuffling the values of a feature, and the other one has to do with node purity, like how these nodes are split in the trees. But I think it's recommended, at least I read a very well argued blog post about how it's recommended to look at the accuracy version of it, where you shuffle the values of a single feature at a time, and then you see how much worse the accuracy gets. So here we have that the number of rooms, the average number of rooms, is the most important according to this. And then LStat, which I think is some percentage of low status inhabitants, according to some definition that I don't know. Percent lower status of the population. And I mean, that's one way to do it, which is perfectly okay. There are some versions of this in the Daleks and IML packages, but we're going to use them for other things. But then there is this random forest explainer that I showed the vignette for, where the woman who made that package argued, I think it's her master thesis or something, and she argued pretty well for a different way of looking at the importance, which is based on looking at how early in the decision tree building process it splits on a certain feature. So you look at kind of the distribution of when a feature first appears in the decision trees. And that will give you a nice plot like this, which is actually not agreeing with the other one. It thinks that the low status feature is, well, so here it's good to have low values, because then you're used early in the construction process, and the number of rooms is the second most important feature, and the next one is quite far behind. This is already pretty nice to show to clients, but then you can also continue and try to look at a feature's influence on the target, which you can do with partial dependence plots. And here I use the PDP package first, PDP for partial dependence. And here what you do is basically you select the feature that you want to look at, like LStat in this case, and then you force it, you choose like a grid of values that you want to force it to have, and then you insert that value into all of the training examples and do the prediction and see what output you get. So it's like an average partial dependent, an average response sort of marginalized over all of the other variables. So here it's apparent that the higher the percentage of lower status citizens, the lower the mean prices will get, but it's not a linear relation. It's some sort of non-linear thing.